Example 2. Graph y equals x, 1 over x plus 1. I'm going to show you two different methods. One's super easy and super fast, and one of them is super thorough and slow. So let's start with method 1, table of values. We're going to set up our table giving our x value, and then we're going to find out what happens when x plus 1 happens. This is our y, by the way. And then what we're going to do is we're going to find the reciprocal of that, 1 over x plus 1. If you're just looking at this and remembering the first example, we know that there's going to be a vertical asymptote at x equals -1, because that's where the non-permissible value for this rational function is. So I'm just going to plunk in some values here. Now, I would like to say that they're random, but they're not. They're based on like lots of experience, graphing stuff. So I just want to you can make up these values, though. That's what I'm saying. They're not random, but you can make them up. Usually I like to hover around -3 to +3. This time I think we're going to be fine if we just go up to +1. You'll see what I mean in a second. Because you want to have enough values here to kind of show the shape of the graph, but you don't want so many that you're calculating, you know, these table of values all day. So if I have x equals -3, and I say -3 plus 1, I get -2. If I take the reciprocal of that, I'm just going to go like that to keep them separate. 1 over x plus 1, that means -1 over 2. So my point on the rational graph will be -3, -1/2. If I say x is -2 and I want to find out what x plus 1 is, I'm going to get -1, because -2 plus 1 is -1. The reciprocal of -1 is simply -1. So the graph, or the point on my rational graph, is going to be -2 from my x and -1 from my 1 over x plus 1. With this one right here, if I plunk in -1 here, I get -1 plus 1, that's 0. If I go 1 over 0, not defined. Which is cool, because from the previous example we know that there's an asymptote, a vertical asymptote happening at x equals -1. Well, look at that. X equals -1, not defined. Perfect. If I put in 0 for x here, 0 plus 1 is 1. The reciprocal of 1 is simply 1. No problem. So the point on my graph is going to be the x coordinate, 0, comma, 1. If I plunk in 1 for my x, 1 plus 1 is 2. The reciprocal of 2 is 1 over 2. So I have the point 1 comma 1 because of my x, 1 comma 1/2. Okay, so let's graph this thing. Oh, yeah, there we go. Love that copying and pasting. Oh, come on, buddy. Get into the frame. So what I am going to do here is I am going to have a dotted line happening at the vertical asymptote. X equals -1. I'm going to just do that in a different color, just so it kind of shows up nicely. So I'm going to go do 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 psh, psh. And what the other thing that I'm going to do is I'm going to extend the horizontal asymptote this way, and horizontal asymptote this way, because no matter what value, let's look at the original, no matter what value you put in for x, this will never become 0. That's the whole point of an asymptote. It gets closer and closer and closer, but never actually touches. So if I'm going to put these points on negative 3 comma 1/2, sorry, negative 1/2, so negative 3 comma negative 1/2 right there. I have negative 2 comma negative 1, negative 2 comma negative 1. And I have 0 comma 1, 0 comma 1. And I have 1 comma 1/2. 1 comma 1/2. Now if I wanted to, I could have another point here, maybe at negative 1/2 or at negative 1.5, but we know from the previous example that the behavior of the graph this way is asymptotic, and the behavior of the graph this way is asymptotic. Now I don't quite like the way that I drew that. There we go. Because it looks kind of like it's curving away, but you always want it just to get closer and closer and closer. This one right here, we get super close, but never touch. Super close and never touch. And this right here is our graph. So this is method number 1, table of values. I'm going to show you another way. So method 2. Using the line. So I'm just going to paste here another graph. I'm going to graph. Oh, I don't want that. I want to see the line. There we go. So I'm going to graph two things. I'm going to graph y equals x plus 1, and I'm going to graph y equals x plus 1, which is all over, or all under 1. First things first, though, I'm going to graph this guy in green. Psh. X plus 1, I know my x-intercept is 1, and from there I have a slope of positive 1. So this right here is my line. Just going to draw that in green. It's not easy being green. Come on, buddy, slow down. There you go. There you go. Now I'm just going to fix this guy just a little bit. Perfect. So that's my original line. But what I want to do is I actually want to graph this guy. So first things first, I need to add my vertical asymptote in. Now the vertical asymptote actually happens when the y is 0. What do I mean? If I said that at x equals negative 1, that would mean that y for this guy would equal 0. When I take the reciprocal of, or if I plunk it into this equation right here, 1 over 0, we have an asymptote occurring at that point. So whenever the line crosses the x-axis, this is exactly where our asymptote is going to be, a vertical one anyway. So I'm just going to draw this guy in right there. Okay, now the next thing that we're going to do is we're going to find those invariant points. Now for example, this guy right here is an invariant point. Why? Because when you go from x plus 1 to 1 over x plus 1, it's the same thing. That's always going to happen at negative 1, and it's always going to happen at positive 1. Remember, that's when y equals positive 1 and negative 1. So on this graph, when y equals positive 1, so it's right here, when y equals positive 1, it's right here. So this right here is our invariant point. And the line right here, when it is negative, when y equals negative 1, here's another invariant point. Now there's another important asymptote that I forgot to draw in, and that is my when y equals 0 asymptote, like that. So literally I can take my invariant points and I know that it's gonna go like this. And it's going to go like this, do, 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 as close as can be but never touches. This guy right here goes do, 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 close as can be to that asymptote and never touches, do, 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 close as can be without ever touching.